Hello, my name's David McLaren. I'm a Senior Consultant for Pinion Advisory, and today I'm going to present a presentation that goes through the critical steps of the irrigation design planning process. So the irrigation planning process, I'm going to talk about 6 components, and these components are as follows. I'm going to start off with number 1. We're going to have a look at the review of your farm natural resources. We're going to look at the financials, return on investment. We're going to look at making it work, like the skills and capability required. We're going to talk through the irrigation design steps. We're also going to look at the existing irrigation systems where principles for new systems can still apply to existing irrigation systems. And then the final component of the planning process, we're going to look at reviewing irrigation quotations. Ask the right questions. So I personally think that when it comes to the irrigation planning process, good irrigation system design is achieving the right balance between economics, agronomics, and the environment. So the natural resources. So it's really important that we start here and talk about the natural resources. So when you're going through the planning process, what access to water do you have? Do you have existing water allocations, and where are they located? Then think about on your property where to irrigate, and then also land capability. Where are the best soils on the property? Determine the potential short-term and long-term sustainable crop rotations. Look at your soil limitations. What soils do you have? Soil type, soil depth. What is the readily available water capacity for that soil type? What's the slope? Is it steep? Is it flat? Is it moderately sloped? Look at the frost risk, the water infiltration rate for the soil type. These are all critical things to understand as part of the planning process for irrigation. Then you can use soil maps, simple soil reconnaissance, or you might just decide to do an EM soil map survey. Also, as you think about irrigation, consider and plan drainage. It's a really important step to consider. Then we're going to have a look at the water budget. How much water do you need, or how much water do you have versus how much you need? And then this final step here, when it comes to natural resources, is really important. So get help. It's so important that you reach out. Use people with the expertise and skills, someone like a knowledgeable agronomist or a soil scientist that can help you through or help you navigate this space when it comes to looking at natural resources. Financials, really important. So know your potential crop rotations and returns. Compile development budget. So what's it going to cost if there's X amount of hectares that you want to develop for irrigation? What does that cost? And don't just look at the hardware cost, look at the complete cost. So important to include things like if there's a center pivot going on a site, fencing, new fencing, additional drainage is required. There may be drains or streams that the pivot has to cross, so there might be bridges or crossings. So it's so important to look at a complete budget that looks at everything to develop the irrigation system on your farm. Then know the operational costs. So look at what access you have to labour and quantify the cost of that. Also the energy. Is it, do you have access to the grid? Is it electricity, diesel, wind, solar? Look at the energy cost. And then also the maintenance cost. What's every irrigation system, regardless of irrigation type, whether it be fixed sprinkler, center pivots, drip irrigation, you name it, every irrigation system requires maintenance. So what is that maintenance going to cost? Then I've got here a point here that says, look at the sensitivity. Will it make money if the inputs or output costs change? Again, reach out to a financial advisor or those with the relevant experience and get help if required. Detail a business case. Does it stack up? Does it add up? And what's it look like on paper? Ensure that you can make money before proceeding. After the financials, we then jump into making it work, where we start to look at the skills and capability. Do you have the necessary skills and capability to make it work? Can you learn the skills to make this profitable? Often we find that the skills are missing, or that the key skills required to make it work are missing. Got a point here that poorly established and managed irrigation systems, they propose a significant risk. And also just adding water doesn't always result in more profitability. So this is really important when it comes to stepping through the irrigation planning design process, because often we see the right skills are missing, but again, it's about reaching out and finding those skills to make it work and ensuring that you can before proceeding. Now I'm going to jump through the irrigation design steps, and we start off with the first step in the irrigation design step is determine the system capacity required. So when we determine the system capacity required for the irrigation system, this gives us a design flow rate. Once we have a design flow rate, we can then determine pipe sizes, pumps, and all the other equipment and incidentals to make the system operational. So system capacity, what is it? Often a question is asked, what is it? So let's just define what we mean when we're talking about system capacity. The system capacity is the maximum possible rate at which a machine can apply water to the irrigated area. It's expressed in millimetres a day. It's not to be confused with the depth applied per pass. So someone might say, oh, I just did an application and put on 6 mils. Well, we're talking about millimetres a day. Often when it comes to centre pivots, you hear service providers and farmers talk about a pivot has a pack size of 6 mil, 8 mil or 10 mil. That is the system capacity for that machine. So it's the daily pumped flow rate in megalitres a day over the area irrigated in hectares times 100 equals millimetres a day. So if you've got a 30 hectare pivot and it has a pack size of 6 millimetres, that means it can put 6 millimetres a day over that 30 hectare area. I think that the system capacity equation here just really simplifies it. So that's what system capacity is. So with system capacity, it's like anything. It can be overdone, it can be underdone, and there's implications of going either way. So at the end of the day, what we're trying to do with system capacity is determine it and size it correctly to meet the maximum crop water demand. So regardless of the crop you're growing, poppies, pastures, potatoes, whatever the crop is, that particular crop is going to have a maximum crop water demand. And it's so important that the irrigation system can meet that maximum water demand. We can definitely draw down soil moisture reserves, and when it comes to drawing down soil moisture reserves, that's when we talk about readily available water, and that's basically just the water available within the crop root zone. So if the crop has a 10 centimetre root depth, a 20 or a 30, it's about the depth that crop can access water within the root zone. System capacity, let's talk about the implications of it being underdone. So if a system capacity is not right and it's underdone, that can result in plant stress at key times. It can reduce in the crop being stressed. It can result in reduced yields. So they're just some of the implications of undoing the system capacity. Then if it's overdone, there's also issues. So you can end up spending way too much money on capital, like bigger pumps and pipes than required. You can have increased application rates. You can have the average application rate at the end of the pivot being too high, lateral movement of water, wheel rutting, and a host of other issues. We'll unpack some of these issues later in the presentation, but what's important is that we need to consider what we're irrigating, crops versus pasture, understand that we need to meet the maximum crop water demand and get the system capacity right. So on this slide, I'm just going to talk through a metric-based approach to system capacity. So let's just go through a scenario of getting it right. So often when we're sizing an irrigation system, we'll look at 30 years of data from silo data. So if we're irrigating in Cressy or Longford or wherever the location is, let's look at 30 years of data and then look at derive the 3 peak consecutive day ETO averages. So evapotranspiration, so when I refer to ETO, I'm referring to evapotranspiration. And that's really, I'm just going to pause there and just articulate what that is. So ETO, it's a calculated parameter and it is calculated looking at the temperature, solar radiation, humidity and wind speed. So we're going to look at in that local area which we want to irrigate, how often for 3 consecutive days do we achieve an ETO of X. So the likely reoccurrence of the 3-day average ETO in a season. So in this graph here, we've got the exceedance for Longford. So the average daily ETO for January was 4.9 mils a day. But looking at this graph here, you can see that, say the ETO is 4 mils a day, it's heavily exceeded. 5 mils a day, number of, down here on the x-axis, you've got the number of 3-day events per year. And then on the vertical axis, we've got the average daily ETO over 3 consecutive days. So basically, once you start to get to 6.5 to 7 mil, it's very rarely exceeded. So when it comes to system capacity, you look at this 30 years of data and say, well, you know, you could go to 7 to 8 mil per day is going to be a sensible system capacity for that machine in this area based off 30 years of weather data. On this slide, it's just don't let power rule you. So it's really important as we design a system and size it that we don't just get focused on power. And some of the key fundamentals here are don't get caught up trying to just use off-peak power. Pumping costs should never be put before the crop. So it's really important here that when we consider like a tariff in Tasmania, say tariff 75, during the summer period, summer is generally for tariff 75 is 1st of October to 31st of March. The peak charge disappears and we only have shoulder and off peak. And I think it's there's 168 hours in a week, so 75 hours of the week are at shoulder and 93 hours are off peak. So the average cost of cents per kilowatt at tariff 75 is probably about 20 cents per kilowatt hour. So it's, don't get focused. The key take home message here is focus on the crop. Don't just get focused on trying to justify off-peak power because it often doesn't stack up from a numbers perspective. So manage system capacity. So already in the presentation today, we've talked about system capacity and what that is, the amount of water it can apply over the field area in 24 hours. Managed system capacity is slightly different. So system capacity looks at that 24-hour period, where a managed system capacity looks at the following components. So peak crop water requirement in mils a day. It starts to look at the application efficiency, so the proportion of water, of total water that can be applied that the crop can use, and available operating hours of the system. And when we talk about that, that's called the pump utilisation ratio. So basically, what managed system capacity is that there are losses. Every irrigation system, there are losses, and you can see based off this picture here, you have canopy evaporation, you have wind drift, and you may have some runoff. So there's losses. So 100% of the water applied doesn't make it to the crop root zone. So there are some losses associated, and that's what application efficiency talks about. And then often we don't utilize the full 24 hours in a day. So there may be, in a cropping scenario, there might have to be herbicides applied, fungicides applied, whatever. So we may not have the full 24 hours. We may only have 18 to 20 hours in a day because there's other activities that have to happen under that irrigation system. So managed system capacity just takes into account these three components. What is average application rate? And it's often referred to as AAR. So average application rate is the rate of water application over the wetted area. It is an average value assuming uniformity within the wetted area. And that's a direct quote from the Nelson Handy Pocket Guide. So pivot, center pivot average application rates increase with the higher flow demands required at the outer portion of the center pivot. So it's really important, average application rate, because it should be compared to the soil infiltration rate. So earlier in the presentation, we looked at the natural resources and looking at soil types and readily available water and soil infiltration. So important, because if the average application rate of the system that's applying water to your given field area, if the average application rate in the outer spans of this center pivot is significantly higher than the soil infiltration rate, runoff will occur. And the question is always asked, well, what can you do to reduce this? So there are options. It's important to investigate options to reduce the average application rate. So the system capacity, the pivot length, and the wetted diameter of the sprinkler are the three levers that we can, or the three mechanisms we can do to reduce the average application rate. So the implications, I think, is a good slide here just to talk about the implications of exceeding the infiltration rate of the soil. So if we're exceeding the infiltration rate, we can end up with soil damage. We can end up with runoff. We can end up with scouring and erosion. We can end up losing nutrients, so loss of fertilizers and all the capital inputs that we put into the system, we can lose those. We can end up with excessive waterlogging of the root zone in low-lying areas, and all of these things can result in yield penalties to the crop. So it's a vitally important issue to understand. So now I'll just unpack those three levers when it comes to changing average application rate. We have system capacity, so that determines average application rate. We can look at the wetted diameter of this selected sprinkler, how far that can throw, and then we have the pivot length. So they're the three levers to pull when it comes to changing average application rate. So let's just talk about the options for the increased wetting footprint. So what we can do is we can select a sprinkler type with a larger throw diameter. so wetted radius. We can look at, consider a higher operating pressure to achieve that. We can also look at over truss rod clips on a center pivot, and I've put a picture here below. Basically, the truss rod clips, instead of just having the droppers in a single line, it starts to stagger them, increase that wetted footprint. We can also look at additional options like boom backs and spreader bars for center pivots, which give us a bigger wetted diameter. I'm now just going to look at calculating the average application rate at the end of a 620 meter pivot. The system flow rate is 277 cubes an hour. The pivot area is 120.76 hectares. And what I want to show you here is just the difference between a 20 meter, a sprinkler with a 20 meter diameter versus a 10 meter, and what it does to the average application rate. So in the first equation here, we have the system flow rate, 277 by the length, 620, and then divided by 120 by 1.59 by 20. So it equals we end up with an average application rate of 44.7 mils per hour. And then we reduce that from 20 meter throw radius to a 10 meter, and we end up with nearly 90 mils per hour. So significant difference between those two just on the sprinkler type and throw radius. So we're going to continue on through the irrigation design steps. So I've talked, we'll now jump into the next one, which is consider the system types available and their suitability. So that, what access to labour, energy usage, water use efficiency, land use efficiency. Then once we've considered the irrigation system type and the implications of all of those things, like how expensive it is to operate with labour, how expensive it is to operate with energy, water use efficiency, how well does the system put down water, land use efficiency, etc. So, we all know there's different types of irrigation systems. There's fixed sprinklers, there's towable laterals, there's centre pivots, but by far, centre pivots are the most efficient when it comes to labour and energy of all the systems out there. Then we can proceed with the irrigation design steps to general layouts. So it might be pivot circles across the farm. Where can we fit them based off all the other considerations? We can fit X amount of circles here or traveller runs here. Then we can investigate the application technology, like what sprinklers and what pressure, and continue to proceed on the critical design steps. Then step number 5 in the irrigation design is development staging. So when it comes to designing an irrigation system on your farm, you might have limited capital in year one. So you might block it up into different stages and say, well, this part of the farm I'm going to develop this year. This is stage 1, this is stage 2, this is stage 3. And it's really important if you're going to develop into staging like that, that stage 1 is correct, because it might use the same pump shed and pipe for the following 2 stages. So developing in stages is commonly done, but it just needs to be well thought out. Then you might look at grouping irrigators based on pumped heads. So if you've got center pivots at one area of the farm that are the highest lift, you might put all those together. And then if you've got another group of center pivots that are really low head lift down on the flats close to the pump shed, you might group all those together and split those off. So you put all the high head machines together and all the low ones together. So you can start to look at efficiencies there. Then with the pipe routes and sizing, really important, you might look at what pipe sizes I need, and that's going to be determined off flow rate through the pipe, what velocities are in the pipe. Pipe sizing is absolutely critical. And then you also might look at, what routes, like what's sensible. Is there a rocky knob that you've got to bypass? Is there forestry on the property? Think about the alignment of the pipeline, the sizing, and sizing the pipe, and the correct sizing of the pipe has massive implications on energy efficiency. Then the next step is looking at pump station design, and pump station design is another critical one. So where's the pump station going to be designed? Obviously, you don't want to put it in a flood zone or too close to the river, but you also need to consider access to the pump shade, good layout and design. Is it serviceable? Is it accessible? Do pumps need to come in? Do pumps need to come out? Really critical things for ease of maintenance and efficiency with good pump shed design. Then it comes to step number 6, like energy efficiency of the system. So I've already discussed pipeline efficiency, like flow rate and the velocity in the pipeline. But also you want to select motors with a motor efficiency. So basically you're looking to optimize the system to run effectively, efficiently, because if it doesn't, it's going to cost you money in terms of energy for the duration of the system. Then the final step might be you start to look at system controls and monitoring, like what level of automation do you want? What controller do you want? What inputs do you want measured? Do you want pressure monitored, flow rate monitored, voltage monitored? There might be some key criteria that you want monitored that's critical to your business, and that's really important to identify so you can select the appropriate hardware and sensors for monitoring. So now I just wanted to touch on existing irrigation systems. So the same principles apply. All the principles I've articulated and talked about today, I think they apply for new systems in the planning stage, but they can also apply for existing systems. With existing systems, my philosophy is you need to measure, to manage labour and energy costs. You need to actually, quantify these, measure these. What are they? And then start to sort of ask questions like, has the machine been audited? Like you drive past the machine and it's putting on water, but have you actually measured any outputs or tried to define how well the machine's performing? So have you measured the pressures? Have you checked the flow rates? Have you put some catch cans or rain gauges under the machine? So you go to the machine and you set it on 6 mil, but is it putting on 6 mil? Or you go to the machine, put it on 10 mil. Is that what's getting to the crop, or is it performing poorly? So check the sprinklers. Are they alive? Are they rotating? Are they performing? Is the machine with panel calibration? Is it walking X amount of meters per minute? So when you start to measure to manage, is you can start to assess an existing system and say, well, an existing system should be an asset. An irrigation system that's performing should be an essential asset to the farm and critical to the farm business, but is it a liability? And then once you've done some measurements in terms of, a farm staff going out there every second day to fix sprinklers and put repair gearboxes and repair leaking spans, and all of a sudden you're spending a ton of labour and input. So answer that question: is it an asset or is it a liability? Is it susceptible to breakdowns? Is it time for an overhaul or an upgrade? And I think this quote here is relevant. There's no such thing as standing still. You either move forward or regress. So an irrigation system isn't set and forget. It requires maintenance. You need to measure to manage, and it will quickly become apparent if it's an asset or a liability, and you can step through that once you've got some measurements off the machine. Reviewing irrigation quotations, I think it's really important to ask the right questions. It's so important. So what is the system capacity? So when you get a quotation of supplier A, supplier B, or C, ask questions like this: what is the system capacity? What is the sprinkler package average application rate? For example, if it's a huge machine with a high system capacity, is it likely to create lateral movement of water and runoff, erosion? And if you can't get the water into the crop root zone, you've effectively failed. What are the number of sprinklers on the machine? The expected annual operating costs. So in terms of labour and energy, what's the pumping cost per megalitre? Is the specified machine operating within the manufacturer's slope limits? That's a big one for Tasmania. Often we have hilly and major grades. We might have slopes with 25, 28, 30% grades. And all pivot manufacturers will specify a maximum slope limit for that machine. And if it's outside of that, you're outside the operating limits of the manufacturer, and your warranty is not going to apply. So it's really important that you've got a machine on that field that is fit for purpose and is designed and specified for whatever slopes it's operating in. What are the design pressure at the pump and irrigator? What are my pipe sizes? What are the pump and motor efficiencies at the duty? Sprinkler type, is it Nelson? Is it Comet? What is it? Does it have part circles fitted for dry wheel tracks? Does it all add up? I think it's just really important here to just ask intelligent questions as you go through reviewing irrigation quotations, because it's often a significant investment, and it's really important that you don't just tick and flick. It's think about what the machine's going to do and ask the right questions. So in summary, we have some take-home messages. I think what's really important after going through the presentation today is it's important that you get the fundamentals right, get the resource base right, ask the questions around financials. Does it add up? Does it stack up? Source the right skill set. For example, get the right people on the bus in the key seats. Do you have the right skills to make it work, make it profitable? We've also seen the importance of getting the system capacity right. We don't want to overdo it. We don't want to underdo it. There's implications of under and over. So let's have that metric-based approach to system capacity and think about the 30 years of weather data in the area. What is the maximum crop water requirement, and address that. Don't get fixated on the equipment. There's so many other steps in the process that are really important. At the end of the day, we just want to get water to the crop root zone and maximize yields. Don't just get so fixated on equipment. There's multiple steps required to make a good irrigation system. Concentrate on ensuring the agronomic outcome is achieved. So how vitally important is that? Like, it is exciting to get pumps, pipes and equipment on the farm and develop and have staging, but it's so important that we don't lose sight of the agronomic outcome, and that's getting water effectively to the crop root zone. And I'll sort of come back to that point that I started with, that good irrigation system design is achieving the right balance between economics, making money, agronomics, getting water to the crop root zone, and also good irrigation design shouldn't have or shouldn't be a detriment to the environment. So we don't want to have lateral movement of water, creating sediment, runoff, fertilizers leaching through the profile, all of those ugly implications that can result in over-irrigating. So it's so important to get that balance right with good irrigation system design. Thank you. That's the end.